Good day everyone, welcome to Let Me Engineer You. Today we will discuss Chapter 5, Estimation of Water Demand, which is part of water supply planning and development. Water demand estimation is one of the most important steps in designing a water supply system. Engineers must determine how much water a community needs not only today but also many years into the future. A water supply system that is undersized will lead to water shortages, poor service pressure, and public health problems. On the other hand, a system that is oversized will unnecessarily increase construction and operational costs. Therefore, accurate estimation of water demand is essential for sustainable, reliable, and economical water supply systems. Next slide. The estimation of water demand is a fundamental task in water supply engineering. Engineers must determine the quantity of water required by a community for various purposes such as domestic use, commercial activities, industrial operations, agricultural activities, institutional services, fire protection. In addition, engineers must consider future population growth, economic development, and changes in lifestyle that may increase water consumption over time. This chapter discusses several key aspects, including 1. Classification of water demand. 2. Methods of estimating present and future demand. 3. Different categories of water use. 4. Variations or fluctuations in water consumption. Understanding these concepts helps engineers design water systems that are efficient, reliable, and adaptable to future growth. Next slide. Water demand can be classified into several categories depending on how water is used in a community. Each category represents a different sector of society that requires water. The main classifications include domestic water demand, industrial water demand, commercial water demand, agricultural water demand, institutional water demand, fire demand. Each type has its own consumption pattern, quality requirements, and design considerations. For example, drinking water must meet very strict quality standards, while cooling water in industries may have different quality requirements. Proper classification helps engineers estimate water requirements more accurately and allocate resources effectively. Next slide. When estimating water demand, engineers must consider two major aspects. 1. Present water demand. 2. Future water demand. Present demand represents the current amount of water consumed by a community. Future demand represents the expected water requirement after several years or decades, considering population growth and economic development. Water supply systems are usually designed for design periods of 20 to 50 years, so forecasting future demand is critical. If the future demand is underestimated, the system may become inadequate long before its expected service life. Next slide. Present water demand is usually determined using available data such as population served by the water system, per capita water consumption, existing water supply records, metered water consumption data. A simple formula used for estimating present demand is present demand equals population multiplied by per capita demand. Where population refers to the number of people served by the water supply system. Per capita demand refers to the average amount of water used by each person per day, usually expressed in liters per capita per day, or LPCD. For example, if a town has a population of 20,000 people and the average consumption is 120 liters per capita per day, the total water demand would be 20,000 times 120 equals 2.4 million liters per day. Next slide. Future water demand depends on several factors, including population growth, urbanization, industrial development, changes in living standards, climate conditions, economic growth. As cities develop, water consumption typically increases due to improved living standards, more appliances, increased commercial activities, and industrial expansion. Therefore, engineers must estimate the future population of the service area to determine long-term water demand. Next slide. Several methods are commonly used to forecast future population. The most widely used methods include 1. Arithmetic increase method. 2. Geometric increase method. 3. Incremental increase method. 4. Logistic curve method. Each method has advantages and limitations, and the appropriate method depends on the growth characteristics of the city. Next slide. The arithmetic increase method assumes that population increases by a constant number of people every decade. Steps include: first, compute the population increase during previous decades. Second, determine the average increase. Third, add this increase successively to the current population. The main advantage of this method is that it is simple and easy to apply. However, its limitation is that it does not consider accelerating population growth, which may occur in rapidly developing urban areas. Next slide. The geometric increase method assumes that population grows at a constant percentage rate rather than a constant numerical increase. This method uses the compound growth formula. The steps involve calculating the percentage growth rate for past decades, determining the average growth rate, and applying the compound growth equation. This method is particularly suitable for rapidly growing urban centers. However, it may overestimate population in long-term projections because growth rates may eventually slow down. Next slide. The incremental increase method is considered more accurate than the arithmetic method. This method considers not only the population increase but also the change in the rate of increase over time. The procedure involves calculating past population increases, incremental increases, the average incremental increase. Then these values are applied to estimate the future population. Although this method improves accuracy, it still assumes that past trends will continue into the future. Next slide. The logistic curve method is often considered the most realistic approach for mature cities. It assumes that population growth follows an S-shaped curve, where growth is initially slow, then rapid, and eventually slows down as the city approaches its saturation population. This method accounts for limiting factors such as land availability, economic constraints, infrastructure capacity. However, it requires long-term historical data and involves more complex calculations. Next slide. Domestic water demand refers to the water used by households for everyday activities. Typical domestic uses include drinking, cooking, bathing, laundry, cleaning, toilet flushing, gardening. Domestic demand is often expressed in liters per capita per day. Although drinking water is the most critical use, it actually represents only a small fraction of total domestic consumption. However, drinking water must meet the highest quality standards to protect public health. Next slide. Several factors influence domestic water consumption. These include income level and lifestyle. Higher income households typically use more water. Availability of water supply. Continuous supply systems encourage higher usage compared to intermittent systems. Climate conditions. Hot climates increase bathing and gardening needs. Type of plumbing fixtures. Modern fixtures like washing machines and showers increase water use. Water pricing and metering. When water is metered and priced appropriately, consumption tends to decrease. Next slide. Industrial water demand refers to water required for manufacturing processes and industrial operations. Industries use water for various purposes such as processing raw materials, cooling equipment, generating steam, washing products and equipment, sanitary services for employees. Cooling water usually accounts for the largest share of industrial water consumption, especially in power plants and large manufacturing facilities. Next slide. Industrial water demand has several unique characteristics. First, it can be very large and continuous, especially in heavy industries. Second, water quality requirements may vary depending on the industrial process. For example, boiler feed water must be highly treated to prevent corrosion and scaling. Third, many industries practice water recycling, which reduces the net demand on municipal water supply systems. Next slide. Commercial water demand refers to water used by business establishments. Examples include hotels, restaurants, office buildings, shopping malls, cinemas, banks. Commercial water is used mainly for sanitation, food preparation, cleaning, cooling systems, and landscaping. Hotels and restaurants usually consume more water compared to offices due to cooking, laundry, and higher sanitation requirements. Next slide. Agricultural water demand represents the largest consumer of fresh water worldwide. Water is required mainly for irrigation of crops, livestock drinking water, cleaning animal facilities, aquaculture, small-scale agricultural processing. The amount of water required depends on the type of crop, climate, soil characteristics, and irrigation method. For example, rice and sugarcane require significantly more water than vegetables. Efficient irrigation methods such as drip irrigation can significantly reduce water consumption. Next slide. Institutional demand refers to water used by public and semi-public institutions. Examples include schools and universities, hospitals, government buildings, military camps, religious institutions. Water is used for sanitation, cooking, cleaning, landscaping, and specialized activities such as medical operations and laboratory work. Hospitals typically have the highest institutional water consumption due to sterilization, laundry, and patient care requirements. Next slide. Fire demand is the amount of water required specifically for firefighting purposes. Although fires occur infrequently, fire demand must always be considered in water supply system design. Adequate fire demand ensures protection of life, property, and infrastructure. Fire demand typically lasts between 2 to 6 hours and must be supplied in addition to normal water demand. Several empirical formulas are used to estimate fire demand, including those developed by Kuichling, Freeman, and Buston. Next slide. Water demand is not constant throughout the day or year. Instead, it fluctuates due to human activities, climate conditions, and seasonal changes. These fluctuations must be considered when designing water supply systems. Understanding demand variation helps engineers determine appropriate pipe sizes, pump capacities, and reservoir storage volumes. Next slide. There are 4 main types of water demand fluctuations. 1. Hourly fluctuations. 2. Daily fluctuations. 3. Seasonal fluctuations. 4. Annual fluctuations. Hourly fluctuations occur throughout the day, with peak demand typically occurring in the morning and evening. Daily fluctuations vary between weekdays, weekends, and holidays. Seasonal fluctuations are influenced by weather conditions, with higher demand during summer months. Annual fluctuations are associated with population growth and economic development. Next slide. The peaking factor, also known as the factor of inequality, represents the ratio between the maximum demand and the average demand. This factor is used to account for variations in water consumption. Smaller communities usually have higher variability, meaning their peak demand may be several times greater than the average demand. Engineers must consider this factor to ensure that the system can handle maximum demand conditions. Next slide. Demand fluctuations are extremely important in system design. They influence pipe sizing, pump selection, reservoir capacity, distribution network zoning. A common design principle used by engineers is Average demand determines the source capacity, while peak demand determines the distribution system design. This ensures that the system can operate efficiently under both normal and peak conditions. Next slide. To summarize, the estimation of water demand is essential for the proper design and operation of water supply systems. Engineers must consider multiple types of demand, including domestic, industrial, commercial, agricultural, institutional, and fire demand. Population forecasting methods help estimate future water requirements. In addition, water consumption fluctuates hourly, daily, seasonally, and annually, and these variations must be accounted for in system design. By understanding these principles, engineers can develop water supply systems that are reliable, efficient, and capable of meeting both present and future needs. Thank you for listening.